Okay, so let's tackle the RLC circuit. This problem should prove to be quite tedious since it has the resistor, inductor, and capacitor. There's also a forcing function, and we have a couple of conditions. So I may skip some of the algebra and encourage you to check up on it yourself and maybe leave a comment if I made a mistake. So first, let me go ahead and draw the circuit. So I have a sinusoidal forcing. So my forcing has, and it's all attached in series. So it has this resistor. Let's try to draw a decent coil. So we have an inductor and a capacitor C. And this is our driving force, okay, our potential source. The E of t is equal to 100 sine 400t. Okay, so if we recall our governing ODE, we can go around using Kirchhoff's second law and write all the potential gains and drops and set them all equal to 0, and we come up with this governing ODE, this LQ double dot plus RQ dot plus 1 over CQ is equal to our forcing function. And if we plug in the numbers, let me see, I get 0.1 Q double dot plus 11 Q dot plus, it's just 1 over 10 to the minus 2, so I guess it's just 10 squared Q equals 100 sine of 400t. And let's go ahead and normalize this coefficient on the Q double dot term. I'm just going to multiply everything through by 10. So I get the Q double dot plus 110 Q dot plus, that's just 100 times 10 becomes 1,000. Q equals 100 times 10, 1,000 sine of 400t, sorry. So it's the same system. I just wanted to make the leading term 1. Okay, so let's go ahead first and let's solve for the complementary solution, QC of t. So if I write out the homogeneous equation, I get Q double dot plus 110 Q dot plus 1,000 Q is equal to 0. And from here we write the characteristic, or some people call it the auxiliary equation. I'm sorry, it should be an M plus 1,000 is equal to 0. And if you solve this, you should find your M12. I get, let's see, negative 10 and a negative 100, which says that my QC of t will be C1e to the negative 10t plus C2 e to the minus 100t. So this is just case 1 where we had 2 real roots to the characteristic equation. So here's our complementary part. Let's go ahead and just box that off, because we're going to probably pull that in later when we put it together with the particular solution. Okay, so let's see over here. Let's see 2. Let's solve for that particular solution, QP of t. And I'm going to use undetermined coefficient here. So let's just, I'll assume course that the QP of t is going to look a lot like my forcing function. So that's equal to a cosine of 400t. So the frequency after must remain the same. Plus b, I'm running out of space. Let's see. Let's put it under here. Plus b sine of 400t. So close off the big parentheses. Alright, so next, if we assume this for Q, P of T, you can go ahead and find the first derivative, and then find the second derivative, insert that back into the governing equation, and if we solve for the undetermined coefficients A and B, which we should be adept at now if we're looking at this video, I find that A is equal to, roughly equal to 0.0016. I'm just going to put the dot, it's just so on and so forth, I guess. B is going to be roughly equal to 0.00584, and then I'll put, dot, ellipsis buttons just to, so the solution goes on and on and on. So my particular solution looks sort of like this. I get the, I'll truncate the 3 dots, and I'll just write it 0.0016 cosine of 400t plus 0.00584 sine of 400t. Just an example, so we don't really need all the accuracy, and I want to keep all these numbers. I put it in MATLAB or Mathematica anyway, and it'll keep all the numbers, so there's no real reason to keep it now. At this point, let's see, I guess I want to kind of keep the video somewhat short, so let's box this off. Now at this point I can apply my initial condition after I sort of bring these two solutions together. So let me just go ahead and write my Q of T. So my Q of T should bring together the complementary part plus the particular part. Okay, so I'm just going to write all this stuff together. So I get Q of T is equal to, so I write the complementary part, I get C1 e to the minus 10t plus C2 e to the minus 100t, and let's go ahead and write this. I get plus 0.0016 cosine 400t plus 0.00584 times the sine of 400t. So again, this can be quite cumbersome. There's a lot of tiny mistakes that are easily made, and it's kind of tough to keep up with all this stuff. But anyway, this is now our sort of governing system, if you will, but it's a two-parameter family of curves, and that we haven't specified C1 and C2 yet, so we haven't applied Q of 0 is equal to 0 or Q dot of 0 is equal to 0. So at this point, you could apply the first condition, or you can just find the derivative. So let's see, let me just write out the Q dot of T, and then I'll just tell you what I found for C1 and C2. So I get Q dot is going to be minus 10 C1 e to the minus 10t. I'm just taking the derivative of the first term, and then this becomes a minus 100 C2 e to the minus 100t, and if I take the derivative of cosine, it's going to turn into the minus of the sine sign. So I'll get, and then using the chain rule, of course, a 400 comes out, so I'll get minus 400 times the 0.0016. Cosine is going to change to a sine, and then I have the 400t. And on this term, the sine just, the derivative of the sine is going to turn to a cosine, and then the chain rule is going to pull out a 400. So I get a plus 400 times 0.00584 times the cosine of 400t. All right. So that's a lot of stuff. And from here, let's go ahead and if I apply the conditions, q of 0 is equal to 0, and q prime or q dot of 0, the first derivative on a charge, which is just the current. I'm just saying that the current at time t equals 0 is 0, and that the charge at time t equals 0 is 0. So if we apply those two, let's see what we get. So I get that 0 equals C1 plus C2 plus 0.0016, which I guess we could write as C1 plus C2 equals a negative 0.0016. And when I apply the second condition, I get 0 equals a negative 10 C1 minus 100 C2 plus, let's see, I just wrote 400 times that value that I found for B, which was 0.00584. Okay, it's just some constant. So if I try to align these things, let's see, I get a negative 10 C1 minus a 100 C2, and on the other side I get the minus whatever 400 times 0.00584 is. And if you solve this system of equations, let's see what I find for C1 and C2. I get that C1, again, is roughly equal to negative 0.02776. And I find the value for C2 to be roughly equal to 0.026, so on and so forth. So if I put that all back together again, I should get my equation for the charge Q of t. But of course, if I want the current, I just take the derivative of it. Let's see, I'll get Q of t is equal to negative 0.02776 e to the minus 10t, and of course I really need all that accuracy, of course, it's just an example, plus 0.026 e to the minus 100t plus 0.0016 times the cosine of 400t plus, this is pretty long, 0.0058 sine of 400t.